So we got this cart of mass m on a smooth surface, so no friction. It's attached to an ideal spring, so simple harmonic motion. We pull the cart a distance delta x from the equilibrium, so that's our amplitude. And while the cart oscillates around the equilibrium position, a motion detector collects data to make the following graph of position versus time here. So we get this sinusoidal, we call it, even if it's a cosine wave, shape there, typical of simple harmonic motion. So let's put this graph back up here again, and they're asking for a whole bunch of information here. So first thing is they say, well, what is the period of this oscillation? Well, we see here to get all the way back to a full cycle, it takes 4 seconds. So the period is simply 4 seconds there. The frequency is, if you remember, the period is 1 over the frequency, and the frequency is 1 over the period. So that would be 1 over 4, or 0.25 hertz would be the frequency there. Omega, they want to know. This, you got to use the equation that says period is 2 pi over omega, so omega would be 2 pi over the period. So 2 over the period of 4 would be half a pi, and the unit would be, it's going to be hard to put it in here, radians per second. So in other words, it's turning a quarter of the cycle per second. That makes sense because it takes 4 seconds to turn the full cycle there. Now it says, what is the time for the maximum positive velocity? So on this graph, the velocity will be the slope, and the maximum positive velocity occurs, think about you're trying to find a tangent line, it's the steepest right there at 3 seconds. So 3 seconds right there is the steepest it ever gets in the positive direction. What about the maximum negative velocity? Well, then we're talking about the steepest it ever gets in the negative direction, which would be at 1 second. So that means at 1 second, this thing is going the fastest in the negative direction. So it must be going to whatever they're calling negative. That's right when it's in the middle, and then same thing there for 3 and excuse me, in the positive direction. So since a motion detector, well, this one's actually measuring it going away from you as negative there. Time when the velocity is 0. Once again, we're looking at the slope. And so we want to see when it has 0 slope, like here, here, and here. So all of those 0 seconds and 2 seconds and 4 seconds all have 0 velocities. That is one end of the cycle, the other side of it, so halfway through the cycle and back to a full cycle there. Now, they say, when do we get the maximum positive acceleration? Well, you can think of this as the rate of change of the slope, a second derivative if you've had calculus there. Where is the slope changing the fastest? Towards the positive direction. And right here at 2 seconds, it is changing its slope at the greatest rate there, towards the positive direction of a slope. So when do we get the maximum negative acceleration? Well, both here at 0 seconds and at 4 seconds, we are changing towards the negative direction at the fastest possible rate there. And when is the acceleration 0? So in those times there are 2 brief moments, right here at 1 second and right there at 3 seconds, where we actually have a constant slope. And so 1 second and 3 seconds, we are not accelerating at all. In other words, 1 and 3 seconds are the equilibriums. 0 and 4 seconds are one end of it, and then 2 seconds would be at the other end of it there. So then they say, for the next part, come up with an equation. So here is the general form of the equation right there. You put your amplitude in and multiply by 2 times the frequency. So let's just follow that. 2 pi times the frequency times the time. So our amplitude, if we look in here, is also 4. But it's not 4 because of this, it's 4 because of this right here. So our amplitude is 4 meters. Then you have to check to see if it's actually a cosine wave or a sine wave, and it is a cosine wave. So 4 meters times the cosine of 2 pi, and we found our frequency on the other page. It was 1/4 of a hertz. You could multiply that 1/4 times the t if you wanted to simplify that out. And let's go ahead and do that. And so we would get x is equal to 4 meters times cosine of 1/2 pi times t. And that pi, 1/2 pi, by the way, is a hertz. It is a frequency there. Okay, part C here says, what if another group of students collected this data from the motion? What's a possible explanation for what is going on there? Well, let's see here. It still takes 4 seconds for the same cycle, and it's still going in an amplitude of 4. The only difference here is we're starting at a sine wave here. So this is like they started their machine right at the middle point there, so or at the equilibrium. So they started at equilibrium. So they either started their data collection at equilibrium, or they kicked it from equilibrium, or something like that. So what would change about this position versus time graph? Not much. It would still be the same amplitude. The only difference would be we would write a sine. And so that is the primary difference there, because that's important. Where did we start before we start this cycle over and over again? So on the very last part here then, they say, what if another group, here's our old graph by the way, what if another group put mass in the cart and filled it up till it had a mass of 4m? What effect would that have on this graph that's right here? Well, look at the equation for the period of a mass on a spring. Mass is under the radical there. So period is proportional to the square root of m. So that means if we make this 4m, then to keep it proportional, we've got to make 2 times the period there. So this period is 4 seconds. We can't even fit the full period on here, but we can at least do this. Instead of half the cycle taking 2 seconds, we'll make half the cycle take 4 seconds, and it would look something like this there. So the period would get bigger because it would be more massive and harder to shake there.